A little background here. The spectra of a compound is determined by what wavelengths of light it absorbs. A lot of times, molecules only absorb non-visible wavelengths, for instance, the UV. These are high-frequency electromagnetic waves and high energy. Another important thing to understand is that the energy of the light that's absorbed is equal to the energy difference between the orbitals that electrons are transitioning. For example, here we have a little energy diagram with 4 different molecular orbitals. The molecular orbitals are where the electrons live. If one absorbs a light photon that has just the right amount of energy to raise its energy from this molecular orbital to this one, we get a pi to pi star transition. Let's look at these pi molecular orbitals. A pi molecular orbital is formed from the overlap of p orbitals on each carbon in a conjugated carbon-carbon double bond system. Each of these p orbitals has a positive phase and a negative phase, and we kind of color one dark to show that it has an opposite phase from the light side. So if these two atomic orbitals overlapped, they would form a area of density here and an area of density here, and we could write the molecular orbital like this. Those two atomic orbitals could also overlap in an orientation where there's a node between them, by which I mean the dark side's up on one of them but down on the other. The more nodes there are, the higher energy the orbital is. So the first one we saw was a pi orbital. This one is a pi star because it has a node and it's higher in energy. Another thing to understand about molecular orbitals is that in a conjugated system, the number of molecular orbitals formed is the same as the number of carbons involved. So in this very simple molecule here, there's just 2 carbons, and we saw both of the molecular orbitals. As the number of carbons increases, let's look at this guy. Here there's 6 carbons involved, so there are 6 molecular orbitals. And as there gets to be more and more molecular orbitals, their energies get closer together. So here's our 2 carbon molecule, where there's only 2 molecular orbitals, one here, one here. Light comes in, and it has to be very energetic to be absorbed. It has to have this much energy to bump an electron up to the pi star orbital. So it's very probable that that photon, to have enough energy, has to have a high frequency, and it probably would be in the UV. For this molecule here, the molecular orbitals would look something like this. There'd be 6 of them. The pi orbitals would be on the bottom, pi star up here, and to transition from pi to pi star, a photon would have to be absorbed, and that photon wouldn't have to have quite as much energy. It could be at a little lower frequency than the last example we saw. So this might be a low enough frequency to be a visible light. So maybe it's absorbing blue light. And if one color is removed, then the compound itself is colored. So what we're seeing here is that molecules with these long conjugated double bond systems are colored because they have a bunch of molecular orbitals and they're close enough together in energy so that visible light has enough energy to bump electrons up from pi to pi star orbitals and absorb that visible light. So in an even longer conjugated double bond system, This molecule might absorb multiple wavelengths of visible light. So, an example is of beta carotene in carrots. Your carrots are orange because the beta carotene absorbs colors other than orange. Another example is the rhodopsin protein in our eyes. It has a long conjugated double bond system, and it absorbs blue light, blue-green light. If you look at the molecular structure of dyes, a lot of them will have a conjugated double bond system. Alright, so here's what we've seen so far. Is that this molecule will absorb light and will go, it'll have a pi to pi star transition. It'll absorb somewhat high frequency light. This molecule will absorb lower frequency light, but also in a pi to pi star transition. And let's get to this guy. This guy's special because it has these non-bonding electrons here. There's a couple lone pairs on the oxygen. And if these electrons get excited, it's an N to pi star transition. So this molecule will have a additional absorption band and a pi star as well as the pi to pi star.